All right, here we are. So we've got a lot to do today. We're going to start with the problem sets from chapter 3, which we finished last time. So let me get those open. Actually, let's go get them off of Moodle. Let's see. Uh-oh. All right, so yeah, wow, this is a big pile of material, isn't it? Yes, it is. Now, I don't know what happened. Apparently, you can only put so much in each section in this Moodle. So I've created what I call part 1 and part 2. It just means that this top section ran out of space. So all the new material will come down here for a while. And I guess when it gets full, I'll move it down here and create a part 3. All right. So that's why it's set up like this. But everything's here. And so we have our practice problems. And let's see. Let me just go find them. There they are. Okay, there's number 1. And there's number 2. And so when these are done, we're going to take a peek at chapter 4. All right, we'll see how far that goes. All right, so let's see. First, let me save these. All right, so today's the 29th. And then this one. All right, here we go. Now, these are all to do with, of course, as you can plainly see, imaginary numbers. And remember, last week we spent a lot of time looking at their algebraic properties, some of which proved to be quite interesting. In fact, you know what? Let's do this. Let's go back and open up our notes. I made a little chart in here somewhere. Let's see if we can find it, where we can see the different powers of I. Here, no, not that one. There it is. So yeah, it's very helpful to have this in front of us when we're doing these types of problems, because often it can help us simplify our results quite a bit, as a matter of fact. So I'm just going to leave this here so we can see it or refer to it as we go along, just in case we need it. Now, first things first, here we're evaluating. Now, all that means, of course, is that all the x's are being replaced with 2i. So if you do that, so you'll have 2i squared. So already we're going to need these exponents. Remember, I squared is -1. And then we'll have 2i minus 4. So when we square 2i squared, we actually end up with 4i squared, because you're multiplying 2i by itself twice. Okay, let me just make a little note. Oh, hold on 1 second. Oh. I have to do something really quick. I'm using up all of my USB drives on this computer. I have to do something to free up one of them. Yep, that's it. Okay. All right, so now I can use my tablet and I can write this down by hand. But what I want to point out here is that when you square, where are we? Okay, yeah, this is what I was trying to do. Just a reminder, if you take something like this, 2i squared, what you're actually doing is multiplying it by itself. And so you end up with 4i squared. Now, of course, since I squared is -1, ultimately this will end up being -4. All right, so we just want to be careful with these. Okay. Anyway, so then we have, now of course we then have 2i minus 4, and as you see in the upper right hand corner here, this is -4 plus 2i minus 4. So we end up with -8 plus 2i. Now I do want to remind everyone that the convention in these cases, not that it's that big of a deal, is to try to write the constant first and then the imaginary number second. But you know, if you wrote it the other way around, that's fine. I'll just mention here, by convention, a complex number, which is what this is written as a plus bi. Okay, and remember too that the square root of -1 equals I, which is referred to as an imaginary number. But when you combine it with a real number, and an imaginary number, is known as a complex number. Okay, so you know, it's not a very important distinction, but the word complex typically is taken to mean something like this: a plus bi, where you've got a real part and an imaginary part. But I itself could be considered to be a complex number too, because I is really nothing but 0 plus 1 times I. So the word complex is often used interchangeably with imaginary. And in fact, if you take more advanced math courses and you run into these, usually they're typically referred to as complex numbers, but you know, either word means the same thing basically. All right, well, that was pretty straightforward. Now this one, we're only evaluating fi. So in other words, you replace all the x's with I, and then you evaluate. Now, based on our chart, which we have in the slides, remember I cubed is -I. And you're done, that's it. Now, you know, of course, if you want to be very particular, you could write it as 2 minus I. Either one is correct. But the key to the whole thing is that I cubed is -I, because I cubed is equal to I squared times I. Okay, so in other words, if I squared is -1, I cubed is just if I squared is -1, therefore I cubed must be -I. That's why this is happening. All right, now these are going to get a little messier, of course. Here we have 2 plus I. So we'll start by now. Yeah, this is where it's going to be a little bit messy. We're going to have to use FOIL to evaluate that. And then we'll use the distributive property of multiplication over addition to come up with the value of this second term. So why don't we do this first? If you take 2 plus I times 2 plus I, and you apply FOIL to that, you have 4 2i, 2i again, I squared. But since I squared is -1, you'll end up with 3 plus 4i for this term. Okay, so let's see. Let's continue from there. So f of 2 plus I equals 3 plus 4i plus, now in this second case, 3 times 2 plus I, that becomes 6 plus 3i. Then we have plus 5. And then when we bring these terms together, if you combine the three constants, you'll have 3 plus 6 plus 5, which is 14, plus 7i. All right, does that work? Yes. The key to the whole thing is this FOIL up here, and remember that I squared reduces to -1. Now, if you forgot about that, go ahead, Fernando. Oh, did you want to say something?
Yeah, but I noticed you were speaking, so
Yeah, go ahead.
I just wanted to ask real quick that you can determine by using the FOIL method what, like, if you stumble up across this like specific formula, I guess, or
Well, no, what I mean is that, like, if you use FOIL, this is correct, but you can simplify it because I squared is -1. And you should always simplify it whenever possible. So that becomes this. That's all that is. The FOIL hasn't changed. What's changed is that this I squared is actually equal to -1. And so you should take advantage of that whenever possible. Don't leave higher powers of I in your expression because they simplify so very nicely, as we saw in this chart here. I think you'll agree that, like, for example, why would you leave I to the 8th in there when it's just 1? So whenever possible, whenever you have a higher power of I, you should try to write out the simpler version of it. And that's what happened here. So we had an I squared, but why leave it like that when you can just simplify it to -1? And yes, the real numbers, any number that you encounter is real unless it contains I in it, and then it becomes imaginary or complex. Just remember what it means. I is the square root of -1, which, of course, in the real number line, there is no such number. Okay, we can only have square roots of positive numbers or 0. So this becomes imaginary. Now, I'm pretty sure we had a video about this where the guy was showing how the normal XY coordinate system does not show the imaginary numbers. They're on a different axis, which doesn't exist. But so he said you have to imagine that it's there. But yes, as soon as you see the I, that's a tip off. This is now a complex or imaginary number. Without the I, it's just a real number. All right. But yeah, so remember, our goal in math is always to simplify whenever possible. So here, with these imaginary numbers, we have a lot of opportunities to do exactly that. All right. So now here, well, we'll need FOIL again too, because as you can plainly see, there's a square term in here. All right, so let's do the FOIL. And also here we have to watch it because it's not just x squared, it's 2x squared. So whatever we end up with from our FOIL, we have to remember to multiply by 2 at the end. Okay, so 2 minus 3i squared is this, which is multiplying this expression by itself. And so by applying FOIL, we have FOIL, 4 minus 6i, minus 6i, 9i squared. And then again, we recognize that this is just 9 times -1. So that's what goes into these parentheses, okay? So we can rewrite this now as 2 times -5 minus 2i plus, I'll keep this one in parentheses, 2 minus 3i minus 3. Now we have to use the distributive property for this first one to come up with -10 minus 4i. And then here we can just drop the parentheses. And then we can consolidate these constants with -10 plus 2 minus 3, which is -11. Okay. So I'm going to double check that, make sure I haven't messed it up. Let's see. Well, now let me just double check this. 2 minus 3i squared. Oh, I made it not a typo because of the handwriting. I just realized, no, sorry, I messed it up right here. I somehow, for some bizarre reason, I wrote 2 instead of 12. All right, well, that changes everything, doesn't it? Yes, all right, sorry about that. I knew something was wrong. Okay, so that means this is now -24i instead of what I had. So now all of a sudden, the constants haven't changed. This is now -27i. Okay, now it's fine. All right. So I was just careless when I was writing up here. All right. Now what do we, oh, now look at these. Yeah, okay. Well, this one's going to be a little bit messier because they involve ratios. So the first thing we do is, of course, evaluate it. But when we're done, we're going to have to take one more step. So we'll have 5i plus 1 over 2 minus 5i. All right, and let's be consistent here. Not that this is a big deal. Remember, we're supposed to have the complex, the imaginary number second. Now, normally we don't leave it like this. Remember, our convention is to not have, we try to avoid having imaginary numbers in the denominator. How do we get rid of this? We can multiply this ratio by 1, but expressed as the ratio of the complex conjugate of 2 minus 5i to itself. Let's put it that way. In other words, what I'm proposing to do is take this expression it's hard to explain in English. The complex conjugate, I'll mention it up here, the complex conjugate of, let's say, a minus bi is a plus bi, and vice versa as well. Okay, so these are complex conjugates of each other. So here, I'm going to multiply this by 2 plus 5i over 2 plus 5i. Why? Because, and I'll mention it here, this is the complex conjugate of 2 minus 5i. And of course, this entire expression is just 1. So we certainly aren't changing anything when we multiply this. Now, the reason for doing this is because we're guaranteed that the denominator will reduce to a real number. So in the numerator, we need to do FOIL. to this expression, F O I last all right, but as usual, we will reduce I squared to -1. So this gives us 2 plus 15I plus 25 times -1. So our numerator is going to end up being minus 23 plus 5I. Now, what about the denominator? We have 2 minus 5I times 2 plus 5I. So we have F O. I is -10I. So you can see these two will cancel out. We're left at the end with minus 25I squared. Now, of course, these two drop out. But since I squared is -1, okay, so when we combine these, the final result is that F of, I forgot to write, 5I equals, the numerator is right here, minus 23 plus 5I over 29. So that's as simple as it's going to get. Now, you may have gotten something which is not wrong, just not as simple as it could be. Okay, so that's the final result. Can't get any simpler than that. Okay, now if the 29 could evenly divide into the 23 and the 5, then you could simplify it further, but that's not the case here. So this is it, we're done. Now the next one is basically the same thing, slightly different numbers. Okay, so let's get that one done. Now remember, at some point, we're probably going to need the complex conjugate. Oh, wait a minute. Okay, so let's plug in everything. And right here, this number, this ratio is technically not wrong, but we would like to simplify it. So let's do that with our complex conjugate. Of the denominator, that is, and that would be just 3 minus 4I over 3 minus 4I. Okay, and then we can apply FOIL to both the numerator and the denominator. So we have 3 minus 4I, 24I, and minus 32I squared. That equals 3 minus, plus 20I, because these two add up to 20, minus 32I squared. And of course, the I squared reduces to -1. And as always, we have to be so careful about sign errors. It's just so easy to make a sign error. All right, so that's our numerator. Now the denominator would be all right, so for the denominator, we had 3 plus 4i, 3 minus 4i. Okay, so let's apply FOIL to that. And you'll see it will reduce to a constant, a real number. F is 9, O is minus 12i, I is positive 12i, and then last is minus 16i squared. These drop down. This becomes minus 16. And so this ends up being 25. So finally, after all the dust settles, we end up with our f of 4i equals, well, we know 25 is in the denominator. The numerator, sorry, was 35 plus 20i. Now, in this case, if you really want to get even simpler, not that this is wrong, but if you notice, everything here divides evenly by 5. So I can actually reduce this a little further to 7 plus 4i over 5 if I want to. You know, if you want it to be truly as simple as possible, then that is what you should do. It's not that big of a deal. Okay, just wanted to point that out. This one is fine, but you know, that would be a little bit better. Okay, just because it's simpler. Now here, ooh, these are nice. Well, these are just sums. You can easily add these together. There's no problem there. Nothing unusual is happening here. You just drop the parentheses in this case. 3 plus 2i plus 5 minus 3i. You just end up with 8 minus I. Oh man, that was so simple. What happened? I don't know, but here we go. Let's try this one. So we end up with minus 1 plus 2i. All right. Wow, look at this one. They're so easy. Oh, but here we've got to watch it because we have to distribute that pesky negative sign across both of these terms. So again, we have to be super careful here with our signs. It's negative 6 plus I. All right, if you are not careful, of course, you'll not get the right answer. So this time you end up with minus 11 plus 4i. All right, what about this one? Same thing, we're distributing that negative over these two terms, so be careful. So we end up with minus 1 minus 5i. Okay. Oh, but then the fun ends because then after this one, we've got all multiplications. So the easy ones are done. So here we have plus 6 minus 9i. Again, we have to be careful here. The constants add up to 2. We end up with 2 minus 5i. All right, now let's look at this one. Now this one is easy because you're only multiplying that expression by one term. So you just multiply them both by 4i. But, look at this. There's a simplification here. Because that's, of course, -1, so you end up with 8i minus 12, or you can write it as minus 12 plus 8i. Means the same thing, of course. Now 13, well, 13 is very similar. You're just multiplying both those terms by 3i. So you have 15i minus 6i squared. And then, of course, you can simplify that because negative I squared is -1. So it's either 15i plus 6 or 6 plus 15i. Very good. And now we have now, oh, more foils. Okay. We're good at FOIL. Okay. So let's see. What would that give us? F O I L 8 minus 2i 12i minus 3i squared. Okay, so it's 8. Now these two, of course, combined to give us 10i. But of course, as usual, I squared is -1. So we end up, hold on. Equals 11 plus 10i. All right, now the next one is also a FOIL. So we have 2 minus 3i minus 4i plus 6i squared. Two minus 7i. Now, of course, here we have our usual -1. Okay, so 2 minus 7i minus 6 gives us -4 minus 7i. Beautiful. All right. Now, this one is interesting because you can see that while this is definitely a FOIL problem, these two numbers are complex conjugates of each other, which means that no matter what we do, we're going to wind up with a real number. Let's just see which real number it is. Okay, so F O I last. So these cancel out. Okay, and let's see, that leaves us with 16 plus 4. And as we predicted, it's just a single constant. It's a real number, 20. And again, that's because these are complex conjugates of each other. So this is guaranteed to happen. Okay, interesting, yes. Now, here's some ratios where all we have to do, we're not evaluating, all we're doing is applying that same technique with the complex conjugates. Make that a little bigger so you can see it on your screen here. So we're going to take this and multiply it. So the complex conjugate of that is what we need. And when we're done, we'll have a nice simple result. At the very least, we'll have a constant or real number in the denominator. All right, so let's start with the numerator. So as usual, we'll apply FOIL to it. Six, 3i, 8i, 4i squared. All right, so we'll consolidate the like terms first, and then we'll recognize, of course, this is I squared. All right, so that's our numerator. Let's try the denominator, which is 2 minus I, 2 plus I. Okay, so we're going to start with F. Hold on 1 second. Oh, wait a minute. Okay, so F is 4, O is 2i, I is negative 2i, and last is negative I squared. These, of course, cancel out. And then we end up with 5. So when we bring these together, remember the numerator was 2 plus 11i, and the denominator was 5. That's our final result. Okay. So those are pretty straightforward. And we have another one coming up next, which is very similar. So we'll multiply that by its own, by the complex conjugate of the denominator. Okay, so once again, we'll FOIL the numerator and the denominator separately and then recombine them. All right, F is 4, O is 6i, I is also 6i, and then last is 9i squared. And yeah, I've already combined these two. And then, of course, this I squared is negative 1. So that's our numerator. The denominator, of course, we know it'll end up being a constant. 2 minus 3i, 2 plus 3i. Or 6i minus 6i minus 9i squared. So these drop out. So our denominator is 13. All right, so when all the dust settles, oh, you know what? I just realized I did the same thing again. This is 12i, sorry. I don't know what happened. Everything is right up to this point. I just copied this 12 into a 2. So this is actually minus 5 plus 12i. Everything else is correct. So when we bring these together, we end up with our final answer of minus 5 plus 12i, all divided by 13. That's the final result. Okay, I just did the same thing earlier. It's 2. It's 5, negative 5 plus 12i, not 2. Now, these are a little trickier because you can see that we have to do one extra step here. We need to do a FOIL right off the bat to evaluate the numerator. And then we can see how that maybe potentially reduces with the denominator. So if you take 2 plus I and 4 minus 2i and apply FOIL to it, eight minus 4i plus 4i minus 2i squared. Is that right? 8 minus 4i. Oh, well, that worked out rather well. So you have 10. Well, that, how often do you see that? It's already a constant. So the denominator is 1 plus I. So we've reduced this expression to something a lot simpler. But because we don't want to have an imaginary number in the denominator, the next step then is to use our complex conjugate approach to simplify that even further. Okay, so the numerator, you just have 10 minus 10i. In the denominator, actually, let's not do it like that. Hold on one second. I'd like to write them out separately. For the numerator, that one's pretty self-explanatory. We're just using the distributive property of multiplication over addition or subtraction in this case. But the denominator, of course, we need to use a FOIL. One minus I plus I minus I squared those drop out. So you just end up with 2. So the final result is 10 minus 10I over 2, but you can see that that can be simplified further because this is just 5 minus 5I. So that's one of the simplest ones we've had in a while. Wow, that was nice. I like simple ones. All right, and there's just one more. This one's a bit of a mess, but we can do it. It's a bit of a mess because the FOIL in the numerator is going to lead to a well, no, it's not that messy. All right, it's really no different than what we've been doing. All right, so for the top, the numerator, we'll apply FOIL. Two minus 4I, 6I minus 12I squared. Two plus 2I minus 12I squared. Now, of course, we have -1 here. And this is 12, plus 12. Be careful with that. So we end up with 14 plus 2I as our numerator. So let's write that down. Our numerator is 14 plus 2I. And our denominator is 1 plus 2I. So again, we do need to use the complex conjugate method. So let's see what happens when we do that. Now, of course, we'll have to apply FOIL to both the numerator and the denominator. (14) minus 28I plus 2I minus 4I squared. (14) minus 26I minus 4I squared. And of course, we replace that I squared with -1. Okay. All right. Oh, said did it again. What is going on here? This is 26I. Okay, so it's 14 minus 26I minus 4 times -1. 14 minus 26I plus 4 equals 18 minus 26I for our numerator. Now for the denominator, 1 plus 2I times 1 minus 2I. We're guaranteed to get a constant. One minus 2I plus 2I. -4I squared. Okay, so 1 minus 2I plus 2I. These cancel out. This becomes -1. And so we end up with 1 plus 4, which is 5. So the final result is 18 minus 26I. All over 5. Yes, Fernando.
I see there's -1. What did you do with that?
Which part?
Where you wrote down 1 minus 4 after you simplify from 4 I squared, there's a
Right.
-1, and I want to ask, what do we do with that then? Because I only see that you. Oh wait, I'm sorry, I didn't see that. You multiply that. My bad.
Yeah, we multiply -4 by -1 to become +4. Yes.
My
Okay,
bad.
and then we ended up with 5. All right, very good. All right, so that one's done. All right, I think we had enough complex numbers for one morning. So let's go on to part 2. But now, I mean, these things, they used to be so scary. Now you can see, well, they're just numbers like any others with certain properties that you don't see elsewhere. So I think by now you should be pretty comfortable with these imaginary numbers. All right, but now we're going to go on to number 2. Whoops, number 2. There we go. Now, these are a little bit different because remember, these are all questions about quadratic functions and the vertex form, if you recall, that we can write a quadratic equation in terms of a vertex form. And if you recall, the vertex for a parabola is essentially just the minimum or maximum point. So for example, if this is your parabola, this would be your vertex. And if this is your parabola, this would be your vertex. And the point here, in fact, you know what, why don't we do this? Let me go back and grab the slides where we went over this. Just as a quick refresher. Oh no, this isn't it. Oh, it was here all along. All right. So there's our, yeah. So this part is covered. We're done with all this good stuff. There we go. So here's our quadratic equations, or functions, which are expressed as parabolas. And of course, if the coefficient of x squared is positive, the parabola faces up. And if it's negative, the parabola faces down. And as I just mentioned, oh, and the order, yeah. The order tells us the highest exponent in the equation. A quadratic function or equation means that we have x squared, but that's as high as it goes. Cubic means there's an x cubed term in there. So here we're focusing just on x squared cases. We know that a parabola is symmetrical. It looks like a big U. We know that A is positive, means that it opens up. In other words, it faces up. Or I had a high school math teacher who used to say that this holds water. You can imagine if you left this out in the rain, the next day it would be full of water. And then this one, he would say that it does not hold water, or it faces down. Okay, if you leave this out in the rain like this, and you pick it up the next day, it might be wet on the top. There's no water inside of it. Okay, so the vertex is basically just the minimum or maximum point, which you can see there's one unique vertex for that parabola. The axis of symmetry is just that straight line that cuts through the vertex. The zeros or solutions are where it crosses the horizontal axis. And then the y-intercept is just where does the graph cross the vertical axis. Okay, so now the vertex, we can write our quadratic equation or function in a different form that means the same thing, but it's written in such a way that it's easy to see at a glance what the vertex is. Now, you might think what a pain this is, but for some applications, it's actually very helpful. So the way these letters are written, H comma K is the vertex. In other words, H is the X coordinate of the vertex, and K is the y coordinate of the vertex. All right, so keep that in mind. And then we went through and did some examples. So let's get back to this now. So what are we being asked to do? What we're being asked to do is rewrite it in this form. Now, the way to do this, the easiest way is to do the following. So normally what you do is you start out by saying, all right, well, let's look at this quadratic function. It's ax squared plus bx plus c. That's the traditional setup. Now, in our example here, therefore a is 1. There's an implied 1 multiplied by x squared. B is negative 12 and C is 32. So what you're going to do is use the following relationship. H can be calculated as, oh, let me just remind you one more time. This is the vertex. Okay, this is the x coordinate. And this is the y coordinate. So there's a formula for this, as it turns out. H equals minus b over 2a, which in this case is minus 12 over 2 times 1. Now, k is f of h. So therefore, what you're going to do is take this expression and replace all the x's with 6's. All right, so everyone sees how that works. Once you know what h is, substitute that back into this function, the original function, and that will give you your k. All right, so here that would be -4. All right, so what this means is that the vertex is 6, -4. But we're not done yet, because the function, the general function for this is, let's see, we just had it. This is what you're aiming for. Wait, hold on. A times, all right, let me just copy this. So in other words, now you replace the h and the k, and you'll end up with the same function written in the vertex form. Okay, so you're going to have, so a was 1. So we can basically just leave it out. X minus h, which is 6, squared, plus k, which means -4. So in other words, it's hard to believe, but these are the same thing. So I put it back there so you can see them. Now, I'll just make a little note here. These are the same thing. Now, if you're not sure, now watch this. Look how easy it would be to double check this. Let's try that just this once. Let's double check. If you're not sure, just double check. So here's what you do. Take your x minus 6 squared and FOIL it. X squared minus 12x plus 36. So that means that here, when you write f of x equals x minus 6 squared minus 4, since this is the value of x minus 6 squared, that means that this expression equals x squared minus 12x plus 36 minus 4. And our final result is x squared minus 12x plus 32. And that, of course, was the original equation. It's right there. Just copy that down here again. So what we just did was we proved that we did it correctly. All right, now you don't have to do this every time, but sometimes it might be a good idea. Now for this one, we'll follow through the same procedure. A is 1, B is 2, C is -3, H is minus B over 2A. Okay, H is -1, K is F of -1 then, or -1 squared, plus 2 times -1, minus 3. 1 minus 2 minus 3 minus 4. So even though it doesn't ask the vertex, I just want to point out that the vertex is, some of these cases you will be asked for it, it's -1, -4. So then also remember that the format that we're looking for is this. Okay. All right, in fact, I'm going to copy this into all of these, just so we have a reference point. Yeah, we don't want to have to keep scrolling back and forth 100 times. So that being the case, what you're going to do is write x. Now x minus a -1 is x plus 1. Oh wait, I almost forgot about the a. No, but a is 1, so we don't really need it there. So this is actually plus 1. And that's -4 because k is 4. Okay, so in other words, you're subtracting h, but h is -1, so it's actually x plus 1 squared minus 4. All right. So now we have a couple more, and they're exactly the same. It might get a little messier, but they're the same format, which is kind of nice. Oh, let me just check something. Oh, they just want to make it clear that there, if you say H and K, then it's understood we're talking about the vertex. I don't know why they chose H and K. That I don't know, but the point of it was that you don't want to confuse it with just any generic X and Y. So in other words, if a mathematician sees H and K written down somewhere, they know right away it means the vertex. Okay, that's all there is to it. It's just notation. Yeah, just so that it's clear that we're talking about the vertex. You know, it's like a lot of, in math, a lot of the notation, you know, somebody invented it somewhere along the way and we just keep using it. Like, why is the Greek letter pi equal to 3.141? Who knows why they chose pi, but they did. And so we've used it ever since. So, you know, there's certain conventions that we always like to follow in math because it makes things clear. You know, the whole point of all this is to make information available to you in the clearest possible form. Like, it's kind of like when you're writing an essay, you want to make your writing as clear as possible. Here, it's the same thing. If we're consistent with the way we express things, then that should make it easier for people to follow what you're doing. All right, so, and the interesting thing about math is there have been, it's like notation is sort of like something that can change over time. A lot of it depends on what people find to be useful. And in fact, there were two very great mathematicians named Isaac Newton, who you probably know from high school science, and Gottfried Leibniz, who both developed calculus at roughly the same time. But they used very different notation to explain it. And somehow or other, people just preferred Leibniz's notation. And so that's what we use now, just because people looked at them and said, this one makes more sense to us. So, notation is sort of like, it's like language. Certain words eventually disappear and others take their place. The whole idea of notation is just to make things as clear as possible. So H and K, why H and K, who knows? But that's what we're using just because that's what everybody else does. Okay, so now if this kind of thing excites you, I mean, there's plenty of books out there that talk about these very issues. But for today, we'll just keep using H and K. And so, all right, here's another one. So remember, the first thing you want to do is identify A, B, and C. Now, this one's a little tricky because C is just 0. Okay, it doesn't affect H, though, as you know, because H is negative B over 2A. Okay, so it's just 1.5. I'll just leave it like that. Okay, now once that's been said, f of K equals f of H. So we'll plug these into the original equation. A quarter minus a half. Now, in order to do this, we need a common denominator. So let's rewrite this as a quarter minus 2 quarters. And we're good. So the vertex is a half and negative a quarter. But the form that we need, which I've conveniently put right here, is now A once again is 1. So we don't really need it there. X minus, now H is positive a half, so we'll subtract that. And then we have K. And that seems to be it. Yes, that's it. And by the way, I almost forgot. You know what I'd like to do? Let's go back and take one of these over to Symbolab, just to remind ourselves what this is supposed to look like. I like Symbolab just because it's so easy to, graphing is it's hard. It's an art. And it can take a while to visualize what these things look like. So whoops, plus 2x minus 3. So why don't we just use Symbolab? And so the vertex is -1, -4. How do you like that? That's exactly what we found. Okay. Now, what I'd like to see if it, I'm going to type in x plus 1 squared minus 4 and see how it reacts to that. I want to see how smart Symbolab is. Now, given that this is the free version, well, we'll see how it goes. They will sell you a more advanced version if you want it, but let's see what it can do. Well, we didn't trick Symbolab, did we? No, it understands the vertex form. There you go. So you can double check any of your results. In fact, you know what I'd like to do? Let me see if it can do this. I'm going to try this one as an experiment. You never know what this thing can do. It tries to solve, it tries to anticipate what you're trying to figure out. And it throws a bunch of numbers, information at you. I wonder if one of those, why is it doing this? X squared minus 12x plus 32. I just want to see what it's able to do. Now we know what the graph is. We've already proved that the vertex is 6, -4. But I wonder if it is capable of writing this out in vertex form. without being asked, because look at all the stuff it's given us. Hmm. Wonder what these are supposed to mean. Oh my God. Man, every time I see this thing, I'm more impressed with it. But you know what? Unfortunately, the one thing that doesn't seem to be here is the vertex form. I guess they figure you know how to do that. In other words, if they're basically saying if you know the vertex, you should be able to figure out the vertex form on your own. But man, they have so much stuff here. Now let's look at this one, inverse. Ooh. And they've got the domain and the range. Man. Now there's an interactive. This means you can fiddle with it and see what happens. Like if I change that to 14, you see what I mean? But anyway, so don't overlook this thing. When you're doing the problem sets, you know, you can feel free to consult with Symbolab because I think it helps a lot to be able to see pictures of what you're doing. And, you know, it can double check your work for you too. Now in a test, of course, you'd be expected to show all the steps. So in other words, it can't do your work for you, but it can at least show you if you're heading in the right direction and help you confirm that what you did is correct. All right, anyway, so let's do one more of these. I mean, it's good to know that it's here. All right, here we go. So first things first, A is 1, B is 5, C is -2. Okay, H is -B over 2A. And K is, of course, a function of H. This one's a little sloppy, but we can do it. So we've got 25 fourths minus 25 halves minus 2. So here we'll need a common denominator. Let's choose 4. All right, so you see what I did? Here I multiplied by 2 over 2, and here I multiplied by 4 over 4 to come up with a common denominator. So we end up with minus 33 fourths as K. So the vertex is minus 5 halves minus 33 fourths. And the form is A is 1. This is minus H, so it's plus 5 halves squared. All right, well, it's not pretty, but it worked. Okay. So there we are. Okay. Now, in the next group, we're basically doing something very similar because the vertex is the maximum or minimum point for a parabola. So by saying the minimum or maximum point, you're basically saying find the vertex. So don't be deceived. Now also, let's double check. Let's go back to our notes. The axis of symmetry, as you recall, is simply that vertical line that cuts through your parabola. And so it's no coincidence that x equals minus b over 2a. So essentially what's happening is that you've got a parabola. Let's say your vertex is here. And let's say the vertex is, I don't know, let's say 2, -2. Basically, the axis of symmetry is the line x equals 2. And that's because it cuts the parabola in half. The left and right-hand sides are mirror images of each other. So if you know h, you also automatically know the axis of symmetry. So this question looks much more complicated than it really is. So we'll start by noting again that a is 2 this time, b is 10, c is 12. So let's look for h. And then k, of course, is f of h, f of -5/2. Oh, this is going to be tough. 2 times -5/2 squared plus 10 times, oops, -5/2. 2 times 25/4 minus 50/2 plus 12. Okay, 54. So again, we're going to need some common denominators. So let's go with 4. And so it looks like we're just going to end up with -2/4 or -1/2. Okay, so this time they really do want to know the vertex. HK, which is -5/2 minus 1/2. Now, without the symbol lab, what we can do, at the very least, we can see that because A is positive, that means the parabola is sloping upward. And the vertex will be the minimum point on this function. Okay, so the vertex, now it doesn't ask for this, by the way, but the vertex is a minimum. And then, of course, the axis of symmetry is just x equals -5/2. In other words, visualize a straight line coming through this vertex. So that's all you needed to do. Vertex and the axis of symmetry. Okay. And again, if you want to check out Symbol Lab, just to confirm this, what the heck, let's do it. 2x squared oops, plus 10x plus 12. All right. Right there, -5/2 minus 1/2. And that's exactly, although the way I drew it, it's a little exaggerated how far down it came. But still, that's what it looks like. All right. Now, obviously the others are exactly the same. So let's do the rest of them. All right. So once again, usually our first step is to just identify A, B, and C. All right, let's begin with H. K will be f of H. So you have 2 5/2 squared minus 10 5/2. This is 25/4 when we square it. And then we have 50/4 minus 50/2 plus 4. 50/4. Okay. All right, 50/4 minus 100/4 plus 16/4. So that should reduce to minus 34/4 or minus 17/2. So the vertex is, oops, five halves, comma, minus 17/2. And then that implies that the axis of symmetry is x equals 5/2. That's all there is to it. I know sometimes these are messy, but it's really not a complex process. But once you get used to it, you know exactly what you're supposed to be doing. That does make things a lot easier. All right, so we got 2 more, and then of course the process is exactly the same in each case. Now here A is -1. We have to be careful with that. So H, of course, is minus B over 2A. So it's 2. And K is f of H, or f of 2, minus 2 squared plus 4 times 2 is 3. So this is -4 plus 8 plus 3, which is 7. And so the vertex is therefore 2, 7. And the axis of symmetry is just x equals 2. All right, so this one I'd like to graph it because this is an upside down parabola, which we haven't seen in a while. So you can see because A is negative, this one faces down. So this vertex represents the maximum point on the parabola. All right, here we go. Let's change this one. What is this? Minus x squared plus 4 and plus 3. All right, let's take a look. There it is. Yep, upside down, facing down, and the axis. Yeah, there it is. 2 comma 7. Perfect. All right. So remember what that means. It means that that vertex is a maximum. Now, if this was some function that expressed, for example, the profits from selling X units of a good, that's an important piece of information. That basically means that if you sell 2 units of this product, we'll maximize our profits at $7. So that would be a classic example of a parabola like this. If you try to sell more units, you'll make less money. If you sell less units, you'll also make less money. So this is an important idea. And we'll probably see more of this later on. All right, and then one more. So again, what do we need to know? And so H is negative B over 2A. This is F of H. So 4 negative an eighth squared plus negative an eighth. And then we have 4 times, this is 1/64. Oh, this one's going to be a mess. All right, so we have 4 over 64 minus an eighth minus 1. Now 4 over 64 is 1/16. So here the common denominator would be 16s. So when you add these together, you get minus 17 over 16 for your K. So the vertex is, of course, HK, which means minus an eighth and minus 17 over 16. And naturally enough, that means that the axis of symmetry is that x equals negative 1 over 8. All right, now we can switch over to something a little different here, domains and ranges. Now, if you recall, let's go back and revisit this, but with a quadratic equation, the domain is guaranteed to be the entire real number line. Okay, because if you look at a parabola, any parabola, the domain is the values of x that can go into this function without causing either division by 0 or the square root of a negative value. So for all of these, the domain is all the real numbers. The question is the range. The range is the y values that can come out of this function. Now, here's our vertex. Let's say the vertex is 2 comma 4. Sorry, that would be negative 4. That means that y can be negative 4 and up, but it can't go below negative 4. So the range is everything from and including, by the way, negative 4 up to infinity. Now that's, by the way, that's when A is positive. If A is negative, let's move that over here. Let's say it's something like this. Here's our vertex. And let's say this is 2 positive 4. Now y can only be 4 down to negative infinity. So the domain is still here, and R is, negative infinity up to 4. All right, so we have to keep that in mind when we analyze these. Now, the book gave us formulas to do this with, but what we want to remember is that this 4 is the K in our vertex. So in other words, in the range, we'll have for A is positive, it's going to be, you could write this as K up to infinity, where K, remember, is simply f of h, which is f of minus b over 2a. So in the slides, this is written as minus b over 2a comma infinity. But I'm hoping that by seeing it written this way, you can see why this is happening. And then when a is negative, it just works the other way around. Oops. And so K, naturally enough, is f of h, f of negative b over 2a. And by the way, don't forget the square bracket means that it includes that value. Okay, so that's why it's written that way. So in other words here, oh, wait a minute. No, sorry, I wrote this one wrong. This should have been f of, hold on one second. There we go. So you can see the two are sort of like mirror images of each other. All right, well, with all that being said, why don't we do one? Like, for example, let's try this one. Okay, so in all these cases, we may as well just go ahead and calculate the vertex because it'll come in handy. So we don't have to think about the domain. We can just get that out of the way right up front. But the range requires us to know the vertex, specifically the K. All right, so H is minus B over 2A. And then K. Oh, one more thing, make sure we all note that A is positive. Okay, so that means it's facing up. And so this now, K is the minimum value of Y. All right, so K is f of h, f of -3, -3 squared plus 6 times -3 plus 4. Okay, so the vertex is -3 and -5, which implies that the range is everything from -5, including -5, up to infinity. Okay. All right, so does that work for everyone? All right. So the others are exactly the same. So let me just copy 10 down here so we can see what we're doing. All right, so this one, A is positive. So we're facing up. And so K is the minimum value for the range. The domain is just negative to positive infinity. So let's find the vertex. Careful of that sign. All right, and therefore K is f of h, or f of 1, 2 times 1 squared minus 4 times 1 plus 2. K equals 2 minus 4 plus 2, 0. Interesting. The vertex is 1 comma 0. And so the range is therefore everything from 0 up to infinity. All right, now for this one, let's go check out Symbolab, because it looks like a fun function. 2x squared minus 4x plus 2. There you go. It exactly touches the horizontal axis, 1 comma 0. Perfect. And in fact, it even tells you somewhere in here, it actually helps us see right there. It's agreeing with us. Our domain is, of course, negative infinity to positive infinity. Our range is everything from 0 up to infinity, including 0. So this way, we're double checking. We're not just seeing the picture, we're also double checking. In fact, while we're at it, let's double check this one. X squared plus 6x okay. So we got -5. Well, actually, let's look at it up here. We found the vertex to be -5 comma 0. Sorry, the vertex is -3 comma -5, but the range is -5 up to positive infinity. Perfect. All right, so we're on a roll now. So what about 11? Oops, we don't need this. All right, so we'll do the same thing. So again, we note that A is positive. So whatever vertex we get, K is going to be the minimum value for the range, okay? Okay, so once again, okay, and then K is f of h. 3 times 1 squared minus 6 times 1. All right, so we've got -12. Okay, so our vertex is therefore 1 comma -12. So that means, oh, and I almost forgot, of course, the domain is understood to be range, everything from negative to positive infinity. And that tells me that the range is everything from -12 up to infinity. All right, and why not? Let's just confirm it with Symbolab, 3x squared minus 6x minus 9. So first it tells us right here, the range is -12 up to infinity. So we're correct about that. The domain, of course, is everything from negative to positive infinity. But let's look at the graph. Yep, right there. It's facing up to the vertex. 1, -12 defines the range. Y can have any value from -12 up to positive infinity. All right. So there's one more of these. Make sure I didn't lose my place. Yeah, right here, we're going to put number 12. All right. So and then once again, A is positive. I guess I should have tried some negative ones, but all right. So here we go. A is 2, B is 6, C is -3. Negative B over 2A, -6 over 4, -3 halves, K f of H. So we have 2 times -3 halves squared, plus 6 times -3 halves, -3. And let's clean this up a little bit. 2 times 9/4. Now, 18/4 minus 18 halves minus 3. Let's find a common denominator. We'll use 4. All right, and when we combine these, you end up with -6 over 4 or -3 halves. So the vertex is -3 halves. Oh, wait a minute. Are they both -3 halves? Okay. No, I think I did something wrong. Yeah, I made a sign error. Sorry. This is, no, that's not right. Hold on. Right here, this is not correct. This is actually 18 minus 48 over 4 minus 15 halves. That's more like it. Okay. So that's our minus 15 halves. That is now, because again, this is A is positive. This is the minimum value for the range. And so therefore the domain, as usual, is -infinity to positive infinity. The range is up everything from -15 halves, including -15 halves, up to infinity. And as usual, we might as well double check, as long as we have this technology, and see what this actually looks like. All right, 2x squared plus 6x minus 3. Beautiful. All right. So the range, as we predicted, is -15 halves up to positive infinity. And the graph, yeah, there it is. So our vertex is correct also, -3 halves, -15 halves. All right. Now, okay, so yeah, it's getting pretty late. So I'll tell you what, let's stop here to have our morning break. And then when we get back in about 15 or 20 minutes, we'll carry on with these last 2 sections. We haven't done this in a while, finding the inverse. I know Symbolab can do this. I'm not so sure it can handle this division though, but we'll go through that and see how that works. And when we're done, it looks like we'll have at least some time to start chapter 4 today. All right. So 4 is kind of an interesting chapter because it talks about logs and exponentials. So we'll see how that goes, but it's very, very useful in practice. All right, so we'll stop here for a few minutes. Let's say we'll come back at about 5 to 10 after 10, somewhere in that range. When you had enough to eat, we'll come back and then we'll carry on with the rest of this. Okay. All right, so let's do some of these divisions. Now, this is a lot like what you've seen with constants. It's been a while probably since you used this long division technique, but it works here very well. So here's what you're supposed to do. So we have to think of this as in two terms at a time. So if I multiply x minus 1 by x, that will give me x squared minus x. So that's exactly what I want to do. So I'll put an x here to indicate that I'm multiplying x minus 1 times x and coming up with a result of x squared minus x. Now, what I'm going to do next is subtract that entire expression from the one directly above it. But we have to be very, very careful with the signs, because that means I'm subtracting this one, but this one is actually being added. So that means I have 10x, and then this term drops down, and so I've got 10x minus 1. Okay. And so if I now multiply by 10, let's see. Oh, no, sorry, I was looking at the wrong thing. No, it's 6x. That's right. Okay, now I'm going to multiply this by 6, because x minus 1 times 6 is, of course, 6x minus 6. So when I subtract, this becomes negative, this becomes positive. So what's left is positive 5. This 5 is a remainder. So in other words, what this is saying is that if you take x squared plus 5x minus 1 and divide by x minus 1, you'll get what's on the top here, x plus 6 plus 5 over x minus 1. That's what this is saying. Now, this piece, the x plus 6 is the quotient. The 5 that's left behind is the remainder. So that's what we were interested in. Now, this might remind you of when you were learning how to divide when you were very young. Like if you were told, for example, to do 4 is divided into 245. How did you do that? Well, you start here with 6, because 6 times 4 is 24. You subtract that, and you're left with 5. So in this case, 6 plus 5/4, so that 6 is the quotient and 5 is the remainder. Now, occasionally you'll get lucky, and when you divide these, you'll discover that there is no remainder. Now, just out of curiosity, I want to see if Symbolab can do this. This would be very helpful. Let's see how it handles a ratio like this. All right, so what did we have here? We had x squared plus 5x minus 1 over x minus 1. All right, so I'm just going to say go. And let's see what it does. Well, that's what it looks like, but I'm not so sure if it's capable of doing this, solving this. Well, all right, let's try this button, solve for. Oh, no, now I have to do it all over again. I guess that's what I was supposed to do in the first place. X squared plus 5x minus 1 is all divided by x minus 1. Let's see what it comes up with. Well, what do you know? X plus 6 plus 5 over x minus 1. It did work. Wow. I'm surprised. Honestly, I'm surprised. I'm like I said, I'm learning more and more about this thing, and I'm liking it even more. So yes, so the x plus 6 is as defined as the quotient. The 5 is the remainder. Okay, so wow, very good. So you can double check whenever you have a situation like this. So let's try this one. You have, and by the way, you can always double check if you're not sure. Like for example, here, if you multiply on the right-hand side by x minus 1, you should end up with x squared plus 5x minus 1. But anyway, let's do this one. All right, so we start with 4x plus 2. If we multiply that by x, we'll get 4x squared plus 2x. All right, great. Now, remember, that whole thing has to be subtracted. And that means this first term is negative. This one is also negative. So these will drop out. Oh, wait a minute. No. Yeah, no, that's right. That's right. And so we'll minus 12x plus 6. Now, if I multiply this by negative 3, I'll have negative 12x minus 6. And when I subtract this expression, it looks like they're going to cancel out, but they don't, unfortunately. This becomes positive. This becomes positive. Oh, so we end up with a 12. Okay, so that means that x minus 3 is our quotient. 12 is the remainder. And the problem is basically telling us that this ratio, 4x squared minus 10x plus 6 divided by 4x plus 2 equals x minus 3 plus 12 divided by 4x plus 2. That's what this is saying. All right, now we know that Symbolab can handle this for us, so we might as well double check it. All right, let's go back over there. 4x squared minus 10x four x plus 2. All right, here we go. Oh, that's right, I almost forgot. No, I have it. I hit solve for it. It should be here. Oh no, wait a minute. What's happening here? Wow, did I make a typo? 4x squared minus 10x plus 6, all divided by 4x plus 2. I don't know what it's doing here. That doesn't look like what we have. So it looks like what they've done is they've rewritten it. I guess we'll have to take the word for it that these are the same thing, but I was hoping they would be in this form. So I guess we can't completely rely on Symbolab, can we? No. See, that's the only problem here is that there's so many different ways potentially of expressing this result that, I mean, we can spend some time proving that this is true. I'm not so sure it's worth it. Well, all right, let's just see what this is all about. The first thing I think what they're doing here is, if you notice that here, everything is divisible by 2. So if you were to take and multiply all these terms, yeah, I don't know. This just doesn't seem worth the trouble. I think we'll just leave it like this. This is fine. But I guess it could be rewritten the way they've got it. But I don't think it's worth our while. Let's just leave it like this. I'm very disappointed though. But anyway, let's look at this one. Oh, wait a minute. I think I copied this one wrong. This is a minus. Sorry about that. Yes, it's minus. X minus 3. The only thing I did here was divide out all the 2's, but let's keep this as our final answer. All right. Now this one, let's see, what do we have? All right, so if I multiply x minus 5 by 2x, I'll get 2x squared minus 10x. Let's do that. So this term becomes negative. These cancel out. This becomes a positive. And we end up with x minus 5. Oh, so then we'll put 1 here. What do you know? This one. How do you like that? So in other words, in this case, the quotient is the 2x plus 1, and there's no remainder. So it may not be obvious right away, but x minus 5 divides evenly into this expression. Well, how did we know that? All right, well, so in other words, what this is really saying is that the numerator could be written as x minus 5 times 2x plus 1. And then denominator, of course, is x minus 5. But you see what's going to happen now. These drop out, and your final answer is simply 2x plus 1. Now, I'm sure Symbolab will be able to do this one. 2x squared minus 9x plus 5. All over x minus 5. All right, so the solution is no, they've got something different. Oh my God. Yeah, I don't know, maybe, oh, for God's sake. All right, then maybe there's a typo in here somewhere. I'll tell you what, let's do this one again. I think there might be a mistake here because they don't seem to agree with us. Let's try that one more time. It makes me nervous when I see that Symbolab disagrees with us. All right, so again, if you put 2x here, you're subtracting this, you're adding this. These drop out. This is x, no. All right, I'll tell you what, let's do this. I'm going to multiply 2x plus 1 times x minus 5. I'm going to FOIL this. We're going to find out once and for all who's right. All right. If this gives us back the original expression, then that means we did it correctly. All right, so this equals 2x squared minus 9x minus 5. Yeah. Oh, yeah, no, that's it. All right, well then Symbolab actually did something wrong because this is correct. That's really strange. How did they end up? You know, I'm wondering if maybe this expression actually is correct too. It's just that it's a very odd choice for writing it. Yeah, all right, I'll tell you what, let's not use Symbolab for this stuff anymore. I mean, for the division, because I don't know what's going on there. But we definitely did it correctly. All right, well, anyway, 16, that's pretty disappointing. I was starting to say how great this thing is, and now it does something like that. So, all right, well, anyway, let's try this last one. So we've got 3, let's try 3x, because when you multiply that out, (3x squared). So we'll subtract and subtract. These drop out, 2x plus 14, and then we have 2. These both drop out. And so this is another case where we've got an exact solution. The quotient is 3x plus 2. The remainder is 0. Okay, so let's prove it. If I FOIL this out and it turns out to be this number, or this expression, that means we've done it correctly. (3x squared), 2x, 21x, 14. Yeah, that's it. So this is correct. The quotient is 3x plus 2. The remainder is 0. So this one evenly divides into that polynomial. All right, so let's go on to something else. Inverses. Now, we're getting pretty good at these inverses, I think. Now, remember what we're trying to do here. Y equals radical 2x plus 1. Reverse the y's and x's. And then solve for y. That's what you're doing. And then we can prove that they were correct or not correct. All right, so I'm replacing these, I'm swapping them basically. And then what I'm going to have to do is solve for y, although that looks like it's going to be a bit of a headache. So we'll square both sides, subtract the 1, and divide by 2. So this is the inverse. Now remember the inverse, the original function is this. The inverse is written like this. Now proving this is a bit of a headache, but I think it's a good idea. Let's just quickly run through it. So remember what this is all about. To prove that f and f inverse are inverses of each other, we must show that first, f of f inverse of x equals x, and f inverse of f of x equals x. All right, so remember the original function here is radical 2x plus 1. And we believe that the inverse is x squared minus 1 over 2. So to prove that they're inverses, we'll start here. So we're going to take f of x and replace all the x's with f inverse of x. Okay. And so that gives us 2 times everything here. And let's see if it turns into x. We've got our fingers crossed. Now these 2's cancel each other out. Oh, sorry, I copied this wrong. This is plus. Okay. So these cancel out. X squared minus 1 plus 1. So that one works. Okay. So in other words, I took the original function, radical 2x plus 1. The x is replaced by this inverse. And you can see it simplifies to x. But that's not enough. We have to do it both ways. We have to also prove that f inverse of f of x is also x. So now f inverse is this thing, x squared minus 1 and the original function was, all right, so what we're going to do then is take all the x's in our inverse and replace them with f of x. All right, so the x squared becomes f of x squared. So we're going to have radical 2x plus 1 squared minus 1 over 2. Now the square root squared is just whatever's under the square root sign. So we're going to wind up with 2x over 2 equals x. All right, so that means we did it correctly, which is a relief to know. Let's try Symbolab, even though it's let us down recently. Let's see if it can handle this one. I think it can. F of x. Oh, no. I'm starting to learn how it works a little better. There we go. F of, wow, I'm not sure if I'm supposed to write like that, but let's do this. 2x plus 1. And there it is, x squared minus 1 over 2. How do you like that? So I guess, you know, for certain things it works very well. Other things, not so much. All right, now for this one, same principle. If you write this as y equals radical 3 minus 4x, if you swap the x and the y, and then solve for y, you'll have x is radical 3 minus 4y. X squared is 3 minus 4y. X squared minus 3 minus 4y. And that can just divide out. by the negative 4. All right, so we don't have to prove it every time. Instead, why don't we just run over to Symbolab? And I think you'll see that it is correct. So the function is radical 3 minus 4x. And it should give us back minus x squared over minus 3 over 4. That's right. They just wrote it slightly differently. This is the same thing as it's the same thing. Beautiful. All right. Now, what about this one? So initially y equals 9 plus radical, x minus 4, x therefore equals 9 plus radical 4y minus 4. Okay, so now we have to solve. So this one's a little messier because now when we square both sides, sorry. I made a mess here. Hold on. All right, let me move this down here. X minus 9 equals okay, so now I have to square both sides. Okay, now x minus 9, we can FOIL this to get the square of it. X squared minus 9x minus 9x plus 81. So you're going to have x squared minus 18x plus 81. So that belongs on the left-hand side. And so, yeah, you can see it's a bit of a mess. But remember, ultimately, what we're trying to do is solve for y. So that won't be too bad. All right, so we'll subtract 12, add 4 to both sides. And then I'll divide by the 4. That's it, we're done. But let's check with Symbolab and make sure we haven't goofed something up, because that's always a possibility with these things. All right, so, and of course, there's always a risk that they've written it in a different way. So we'll have 9 plus 4x, radical 4x minus 4. Oh, no, there it is. X squared minus 18x plus 85 all over 4. Beautiful. All right. It's always encouraging when you see that. Okay, 8x squared minus 18x plus 85 over 4. All right, one more, and then we can do something different. One more inverse, and then we can start chapter 4, at least for a while. And so we'll use the following the usual technique. And then, of course, switch x and y. And then, of course, solve for y. All right, so this means that x equals 5 plus radical 6y minus 8. X minus 5 equals radical 6y minus 8. So then I have to square both sides. And we'll come over here and do a FOIL on x minus 5. X squared minus 5x minus 5x plus 25 is x squared minus 10x plus 25. All right, so the left-hand side here is x squared minus 10x plus 25 equals 6y minus 8. So I'll add 8 to both sides. And then finally, I'll just divide out the 6. All right, so let's keep our fingers crossed. See what Symbolab has to say for itself. Okay, so the function is 5 plus square root of 6x minus 8 and ta-da, x squared minus 10x plus 33 over 6 is indeed the correct answer. Excellent. All right, well, that's that. So that was a ton of reviewing, but it was excellent reviewing. So at some point in the next few weeks, I think we have to start thinking about an exam. We'll figure out the details. I think if I remember correctly, last year I did this, the first midterm was based on the first 3 chapters. I'll double check that. I just want to make sure that I'm being consistent with past years. But I think if we try to include chapter 4 in the first midterm, it'll just be too much material. So I will go double check again, but I think that most likely the first midterm will be the first 3 chapters, which means we're basically done with them. So, but we're not going to have it anytime soon. Instead, what we'll do is we'll just start 4, and then maybe the following week we'll do a bunch of review problems, and then I'll post the actual midterm online in Moodle. And what you'll be able to do is download it and do it at home and send me back pictures of what you've done or scans of what you've done. So you'll have a full week to do it. Now, remember, this test was originally meant to be done in class. The time frame, if I remember correctly, was about like an hour and 45 minutes or something like that. I did it over the first half of the class before we had our break. So it's not going to take you a week, but you can have a week in case you need it. But then, all right, so we'll figure this out next week. But right now, what I'd really like to do is get into some new material, which is chapter 4, which is actually a very interesting chapter because, like I said before, it's very widely used material in the real world. Okay, in fact, I've got several real world examples in here because they're easy to find. Okay, some of this stuff, it's very difficult to find examples, not this stuff. Okay, so you can see the title of this chapter is Exponential and Logarithmic Functions. Now, you have seen logs before. Possibly not for a while. You must have seen them in high school, at least in your science classes. You probably saw them in your math classes, of course, but let me just quickly remind you what this represents. Hold on 1 second. So it's basically just an alternative way of writing exponents. So let me just show you some examples. First of all, this is just a quick reminder. Suppose I have a number like 10 to the third power is 1,000. That means what I can do here is write the following. The log to base 10 of 1,000 equals 3. So what this is telling me is that if I take 10 and raise it to the third power, I'll end up with 1,000. Or if I have log base 2 of 32, this equals 5 because 2 to the 5th power equals 32. Now, I don't know if your calculators are able to do this or not. Many of them cannot. I don't really know why they don't put this in here. If you have one of the big ones, the TI 83, 84 series, it probably can handle this. But anything short of that, I don't believe it has this capability. I don't know. Let me just check something. So there's a log button. So maybe, I'm not sure how many of you have this calculator, but there is a way, apparently, of doing this. But anyway, but let's just basically concentrate on how this works algebraically. So the log, and by the way, this number you're seeing here, this 10, is called the base. All logs have a base. And the base can be any number. And so we use them, it depends on what the application is. You see this used in science sometimes. Like, for example, the Richter scale for earthquakes is a logarithmic scale. And so if you hear like the, let's say you were told that the Richter scale for an earthquake is 5, what they're really telling you is that the magnitude of the earthquake is 10 to the 5th power, which is 10,000. No, sorry, it's 100,000. So that's why they say that when the Richter scale goes up by 1, let's say from 5 to 6, the size of, or the magnitude of the earthquake is actually going up by a factor of 10. You also might recall the pH value from high school biology or in chemistry. The pH of water is 7. The pH of an acid is less than 7. And the pH of a base is more than 7. But this pH number actually represents 10 to the minus 7. So in other words, if you're told that the water's pH is 7, they really mean minus 7. So the log turns it into something more comfortable for people. It's more easily understandable if we call it 7 rather than 10 to the minus 7. The same thing with Richter scales. You don't want to be explaining to the public what 10 to the 5th means. So instead, you just call it 5 or 6. Okay, so logs are very helpful in a lot of applications. And so each one has a base, which determines the value. Like you can see here, log base 2 of 32 is 5, again, because 2 to the 5th is 32. Now, there's one base that turns out to be particularly convenient, and that is the number E. So the number E is approximately equal to 2.71828. And you can see it goes on forever. It is an irrational number. And so log to base E is written as ln for natural log. So ln simply means natural log, which means log to base E. it turns out that in a lot of applications, this is more convenient than the other logs like log 2 or log 10. And in fact, we're going to see some of that in this chapter. I've got some examples here which show us how this can be applied to interest rates, which you might find interesting. So with that background, that quick background, and by the way, some books write this as exp of x. This is the exponential function. It's used for cases where, like, say, for example, if we're trying to model the growth of bacteria in a culture, it often follows this because e to the x is a very rapidly growing function. In fact, why don't we take a look in Symbolab at these graphs? Let's do this. Let's first draw a graph of y equals e to the x, just so you can see what this thing looks like. And you can see what it would help if we had a graph. Oh boy, does that grow fast. All right, so it crosses the vertical axis at the point 0, 1, and then it grows very, very quickly, which is what bacteria tend to do. So that's why exponential functions are often used to represent the growth of a colony of bacteria or many other types of situations. But if you notice, the range is 0 up to infinity, and 0 is actually an asymptote. X equals 0, sorry, y equals 0 is an asymptote for this function. In other words, it'll never quite reach 0. So the range is everything from 0 up to infinity, not including 0. In fact, it says it here somewhere, 0 up to infinity, not including 0. But the domain is all real numbers. You can see all the x's can be plugged into this formula without causing any problems. So that's e to the x. Now watch this. Let's change it to log of x. Now look what happens here. Now here the vertical axis is the asymptote, and it grows. If you notice, it's growing at a progressively slower rate. It's like it's running out of energy as we move to the right. It's continuously increasing, but the rate at which it increases is slowing down. Now I'm going to look at this. I want to see if I can do one thing here. I would love to show you both of these on the same axes. Oh, there we go. I was afraid that we wouldn't be able to do this. Well, the purple is e to the x. Pink is log x. The reason why I wanted you to see this is because these functions are inverses of each other. And we'll see more of that later on in the chapter. They're mirror images of each other is what I'm saying. Okay. Anyway, so these both find themselves useful in a lot of applications in the real world. So that's why this chapter is so important. So we're going to start out by writing a very general expression. F of x equals a times b to the x power. And again, we can use this to model a lot of situations in the real world. And a will be defined as the initial value of this function. And why is that? Because f of 0 so in other words, the initial value means f of 0. So that's the starting point. Okay. B is the base, and x, of course, is the exponent. Okay, that's what we mean by an exponential function. Now, the base can be e. It doesn't have to be, though. Any form like this is considered to be exponential. Okay. Now, for this one, the domain is all real numbers. It looks a lot like the one we saw earlier. In other words, a typical exponential function looks like this. All right, so as we saw earlier, the domain would be the real number line, and the range would be 0 up to infinity, not including the 0. Now, having said that, if A is negative, then we would actually have the reverse. In fact, I'll tell you what, why don't we make up some examples? Let's try, and I mean, go to Symbolab. Suppose I start with y equals 3 times 2 to the x power. And so this looks a lot like e to the x, doesn't it? It sure does. But I'm going to change that to negative. -3. Let's see what happens. Oh, it's all below. Now the horizontal axis is still the asymptote, but that's because this function never quite reaches 0 from below. In other words, it's decreasing steadily. So why don't we do this? Let's do the interactive graph. And let's show them both. So you can see they're mirror images of each other. If you can think of the horizontal axis as the mirror. All right. So we can determine the range for these functions by the sign of A. If A is positive, the range is 0 up to infinity. If the A is negative, the range is 0 down to negative infinity. Okay, pretty cool, huh? Look at that, the way it opens up. It's like a flower on the side, a little tulip laying on its side, or maybe a glass, a fancy glass laying on its side. Or it could be looked at a cone, a funnel of some kind. Yeah, I like that one. It's a funnel lying on its side. But anyway, so the range is all positive real numbers. As I said, if A is positive, it's negative. If A is negative, the intercept is always 0, A, and the horizontal asymptote is always y equals 0. Okay, so let's go back to this for a second. It probably mentioned that here. So what they're saying here is that the y-intercept should have been -3. Let's find it. Oh, here it is. Here it is. 0, -3. Exactly. Perfect. All right. Oh, I must. Yeah, this is the Excel version. You can see it's not very good, but it's a good starting point. The Symbolab obviously is designed to do this kind of thing. Now, you can prove that the intercept is 3 by just replacing the x with a 0. And you can see that, yes. And again, remember, we referred to this earlier as the initial value. Initial in the sense that this is the first positive value. All right. So basically with these problems, what we're really focused on is this piece in practice, because this is the quadrant where all the x's and y's are both positive. We may, if we have a function that allows for negatives, then we would do something different. But here, if this is, for example, the growth of a bacteria colony, then this is what we're focused on. All right. Now, any function that behaves like this is said to experience exponential growth. Now, by the way, if you notice carefully here, the one constraint is that b can't be 1, because if b is 1, then this equals a constant. So we have to leave out or rule out the possibility that b is equal to 1. So therefore, because if we did, of course, we would just end up with a constant. So to have exponential growth, anything goes except b can't be -1, a positive 1 rather. And again, A is the initial value. And then B is the so-called growth factor. And related to this, B minus 1 would be the growth rate, which is a percentage. Okay, so we'll see when we go into these examples, you'll see what I mean. Now, what we're going to do here is compare two cases. We have a painting. Let's say we bought a painting, and we want to know how much it will be worth in the future. In the first case, we're assuming that it experiences linear growth. In the second case, it experiences exponential growth. So let's take a look at these two cases. First, here's the painting. And oh, wait, sorry, it's two different paintings. Painting A is worth $100,000, and the annual growth rate is $2,000 per year. All right, so we can write out a function. The value of A at time t is okay. Now I just want to point out t equals 0 means today. T equals 1 means 1 year in the future. So of course that means that t equals 2 means 2 years in the future. So that's how we interpret these t's. Which means that if I try to figure out what the painting is worth today, that's A of 0. Which is just 100,000. So that 100,000 is the current value of the painting. What this is telling us is that every year that elapses, the painting will gain in value by $2,000. Okay, so that's why it's written this way. And you can see this is clearly a straight line. In fact, if I throw this into Symbolab, let's do that. You'll see it's literally just a straight line. And it starts, now you notice how it crosses the horizontal axis, vertical axis at 100,000, that's the intercept. The horizontal axis in this case is time. X is t, okay, X is being replaced with t. The vertical axis is the value of the painting. So if time can't be negative, which of course it can't, we really only need to look at the first quadrant. Okay, so that means as far as we're concerned, the function starts here and works its way up. And you can see every year that goes by, we gain $2 more thousand. All right. It's a straight line. Now B is also worth $100,000, but it grows at a rate of 2% per year. Now, if you notice, $2,000 is 2% of 100,000, but that never changes. So you can probably imagine that this painting will grow more quickly in value than if it just simply grows at $2,000 per year. So what kind of function is this one? Ah, all of a sudden you recognize this as an exponential function. This is A, remember, this is the general form. This is the initial value, or in other words, B of 0. Now this is B. I said before, B is the growth factor. B minus 1 is the growth rate. So if B is 1.02, B minus 1 is 0.02, which means a 2% growth rate. And the exponent is t because this value depends on what time we're looking at. So for example, in 1 year, the two paintings will actually, after 1 year, be worth the same, 102,000. But in year 2, things will be different because this first painting is worth 104,000, but look at this one. Instead of adding $4,000, we're multiplying by 1.02 squared, and so we end up with $104,040. Now, the difference isn't that great after 2 years, but as time goes by, this painting B will grow more quickly in value than A, and eventually it'll be worth a lot more money. So what I did here was I drew, now this is in Excel. Now you can see, it's hard to see, but painting A is this blue one. It's growing at a linear rate. Painting B is this one. And you can see it's not linear. It's growing at an increasing rate. As time goes by, the gap between the two is increasing. So because B is experiencing exponential growth, A is only experiencing linear growth. Now, I think if we go back to Symbolab, we should be able to get this together here. Let's go to the interactive graph, and now B of t will equal 100,000 times 1.02 to the t power. All right, so what have they done for us? Oh, what happened? Oh no, don't let me down, Symbolab. You know what? I'll tell you what, I think I'm confusing it by calling it T. Okay. That's good to know. All right. Now it's happy. All right. Oh, geez, I don't know. That doesn't look right. Huh. That's very strange. I don't. Yeah, I don't know why it's not working properly. Is there a typo here? No. Because this B function has to start. I mean, yeah, it doesn't know that the domain starts at 0, but still. Oh, I don't know. I'm not sure what it's doing there, but it's not working. That's definitely not right. This is what we're supposed to see. All right, well, anyway, forget that. But let's now, in some applications, what we're interested in finding is the growth rate of something or other, like an investment, for example. What if I put $100 in Apple stock 20 years ago? How much would it be worth today? That's a question I could answer with this type of application. So let's say, for example, now here's an example from nature. In 2006, 80 deer were introduced into a wildlife refuge. By 2012, 6 years later, the population had reached 180. If we assume that deer populations grow at an exponential rate, what was the growth rate in that case? Good question. So how do we solve for that? All right, so remember, now we're going to use time in this case. So what we're going to do, because 2006 is the starting year. We're going to let that be t equals 0. And 2012 will represent t equals 12. If you use these two numbers, you're not going to get the right answer. So just be aware of that. These time functions are meant to be based on 0 for today, and every number after that is held for much further in the future. We are looking. So we're going to create an exponential growth function in terms of time. And instead of writing f of x equals ABX, just because we want to reinforce the idea that this is time. Also, the book likes to use n for the number, I guess. T is the function, t replaces x. And so the growth function is this. This should tell me how many deer there are in my refuge at any given time. Now, the initial deer population was 80. And in this context, that's A. Okay, so remember, this is the initial value. But we're also told that in 6 years, the population is 80. And so in this context, that means n of 6, I should say 6, is 80, because this is 6 years in the future. So in other words, n of 6 equals ab to the 6. And we know that n of 6 is this is 180. And a is 80. And we're looking at 6 years in the future. So we're solving for b. Well, actually, we're solving not for b, but for b minus 1. Okay, remember that. B is the growth factor. B minus 1 is the growth rate. So it's easy because I simply divided both sides by 80. And so 225 is b to the 6th power. Now, algebraically, what that means is that 2.25 to the 1 over 6 power equals b. All right, so in other words, that's how I got rid of that 6. I raised both sides to the 1 over 6 power, and I end up with this. And now you just plug that into your calculator, and we end up with a b value of 1.1447. So therefore, b minus 1 is 0.1447. So therefore, the growth rate is 14.47% per year. And that's it. So the deer are growing at a rate of 14.47% per year. And by the way, let's review this real fast. So what I needed to do I raised both sides to the 1 over 6 power, which I'm certainly allowed to do. Anything I do to the left and to the right, if it's the same operation, I do not change anything. But when you have something like this, this is equal to b to the 6 times 1 over 6 power, which equals b to the 1st, which is just b. So that's why I can do this. All right, and so we end up with our answer, which is, of course, 14.47%. All right, now there's another example here. Now this is a fun example. A silver dollar minted in 1899 is now worth $37.42 to coin collectors. What was the annual growth rate between those 120 years? With the understanding that the initial value was $1. Of course, in 1899, a silver dollar was worth $1. So we know how many years are involved. We know the initial value and we know the final value. We can use that information to solve for the growth rate, b minus 1. Now we're going to use a slightly different notation this time. V of t, okay, equals AB to the t. V is the value of the coin at time t. Now, of course, V of 0 is 1. This is A. A is just V of 0. We also were told that in 2019, 120 years later, the coin was worth $3,742. So I can rewrite this as V of 120 is V of 0 times B to the 120 power. And then I can plug in V of 120, V of 0. And now all I'm left with is one variable, which is B. I can divide both sides by 1, I guess. And now here you can see what we're going to do. Raise both sides to the 1 over 120 power. And when you do that, you're going to get 1.0710 equals B. 0.0710 equals B minus 1. So the growth rate is 7.10% per year. So in other words, the value of the coin has been growing at a rate of 7.1% per year for the last 120 years. That's why it's worth $3,742 instead of $1. Okay, so that's what this is all about. So you can see how valuable this potentially could be. It gives you an idea of how fast this thing is growing and whether it's worth keeping. I mean, you know, if you're thinking about selling it, you have to ask yourself, what else could I do with that money? What other asset is there out there that might give me a higher rate of return? If there is no such asset, I might as well hang on to it. But if I found out that the growth rate was only 1% per year, then I might think about selling it because I could get more than that in the, you know, treasury bills, for God's sake. Okay. All right, so now we're getting the sense of what this is all about, what these growth rates are, what this is telling us. Now, by the way, I do want to tell you one more thing. This only works if we can assume that the growth rate is exponential. In other words, if the growth over time looks like this, then we can use this approach. If not, if the growth is linear, then we would be making a terrible mistake by using this approach. So we have to figure out whether or not it makes sense to use exponential data or exponential functions. One way you can test is to find the value at different points in time and plot them and see if they appear to be growing at an exponential rate. That's something you can do to figure out whether this makes sense or not. All right, now, you might recall from your days with the linear equations, if you were given 2 points, and this is only like 2 chapters ago, if you had 2 points, you could easily find the equation of a straight line because we can use this to figure out the slope, and then we can plug that into the formula, and then we can find the intercept. And we can do something like that here too. If we're given 2 points on an exponential function, we can figure out the original equation. The only problem is it's a lot messier, as you can imagine. Okay, it's not as easy as y equals mx plus b. It's a lot messier, but we can still do it. So in other words, you have 2 points. Let's say that would be here and here, and it might be that the function looks like that. So our job is to figure out what this function has to be, and we can uniquely identify this function with just 2 points. But we're assuming that it's an exponential function. If we were told that this was a linear function, well, then we would use y equals mx plus b. But instead, we're going to use f of x equals ab to the x. Now, what I'm going to do first is just pick either point and plug it in, and that's no different than what we did with straight lines. So be aware that this is the x coordinate, which means it goes here. And this is the y coordinate, which means that goes here. In other words, remember, y equals f of x, which means in this case, f of x is 6. And we're also being told that x equals -2. So this is what I end up with. Now you notice there's a problem here. We have two unknowns. But only one equation. So can we do this? No. So here's what we have to do. We have to find our second point and do the exact same thing. Okay, so this time, we will replace the x with 2 and f of x or y with 1. So now we know two things. From the first point, we have this expression, and for the second point, we have this. And guess what? What do we have now? Two equations, two unknowns. Can we do this? Yes. Now, what we can do here, most likely we should use the method of substitution. So here's what we could do. Why don't we take the first expression and solve for a? All right, so here's what I did. These are the two equations. Oh, actually, no, let's do the second equation. It'll be quicker and easier because there's no 6 there. So what I'd like to do is rewrite this in terms of a. And literally, look how easy this was. A equals 1 over b squared. Or if you prefer, you can write it as b to the -2. So how do I find b? I can now put this information right back here. And I'll end up with an actual value for b. This is what it means to use the method of substitution. You solve one of the equations for one of the variables, and then you use that information to solve for the other variable with the second equation. So if you do that, oh, look at that. So now b to the -4, how do we solve for that? All right, I have an idea. Let's multiply both sides by b to the 4. I think that'll be a little bit easier. And so you end up with 6b to the 4th equals 1, which means b to the 4th is 1/6. And then therefore b is the 4th root of 1 over 6. Now that's a messy, messy number. But that's what we have. You're likely to get this kind of thing when you use exponential functions. Now, we can turn this into an actual value. This is approximately equal to 0.6389. So let's do that. Okay, now once we know this, what about a? A is equal to b to the -2. And if you take out your calculator, you'll see that this is approximately equal to 2.449. Well, now we're all set because remember, the function is so we end up with 2.449 times 0.6389 to the x power. And so this is the function that generated those 2 points. It's a mess, but it's correct. Yes, that's a mess. And I've already done the graph for you in Excel. And so let me show it to you real fast. And then we can adjourn to Symbolab to see what it, a better picture of it. All right, let's come over here. Maybe we can identify those 2 points if we're careful. F of x equals 2.449 times 0.6389 to the x power. So we were told initially that it contains the points 2, -6, -2, 6, which would be right about here, and 2, 1, which is right about here. So there they are. And so this is the result. This is the function from which we plucked 2 points. And so that's the final result. All right, well, I did say that that was a lot harder than finding the equation of a straight line, but still, it's the same principle. The only difference is here we have to solve simultaneous equations, which we didn't have to do with linear equations, did we? No. All right, so now what's coming next, and we're not going to do it today, but we're going to start looking at interest rates and how this applies to them. And when that's done, oh, that's going to be fun. More examples, and then we can dive into logs. We can take a closer look at logs. And what we're really interested in here is not just their properties, but how to do algebra on them. All right, and so that's going to take a while, but it's very important. Wow, ooh, there's a lot more to go. All right, so why don't we just stop here? I'll tell you what. So for this coming week, why don't you just make sure you understand all the solutions to the the problem set 3A and B, or problem set 3 number 1 and problem set 3 number 2. Make sure you understand all that. Start reading through these slides so you understand where we're going. And then next week, we'll just pick it up from here, and then we'll figure out the details about the midterm. Now, before we do the midterm, there's going to be another practice problem set, which is called the sample midterm. And that'll give us one more chance to get a lot of practice with all the chapters that we've covered. So that way there'll be one last round of reviewing before you do the actual test. So you'll be plenty well prepared for it. Okay. And then after this, I don't even remember what comes after 4, but we'll carry on from there. So right now, just go home and stay home and relax, and just make sure you understand what we've been doing. And then next week, we'll pick it up from here, and we'll have a full discussion about what's going on with the midterm. Okay. All right. So let's go. And I think we have plenty of math for one day, and we'll see you all next week. Okay. See you later. All right. You can hang around if you want to, Fernando. Or do you want to ask right now?
I just wanted to ask if I could speak to you after class.
All right. Okay. All right. We'll give it a minute for everyone. I know nobody wants to leave this class, but you can see still people are hanging around. All right. No, there's still, oh man, I can't get enough of this stuff. All right. Oh, well, all right. Let's give it another minute. All right. I'll tell you what. I'll assume that they're just, you know, not eager to leave. All right, now it's just you and me. Oh wait, I have to, oh, I'm not sure if I can stop sharing and still be on.
Hi, Professor.
That might be the way to go.
Yeah, do you want to join in another Zoom session?
Yeah, all right, let me turn this one completely off.
Okay.
I'll send you an invitation.
All right, thank you.